Greetings sir and hello everyone. My name is Bengkhong. I'm a junior from the Department of Civil Engineering at Paragon International University. And in this video, I'm gonna explain all the function in the 2D structural analysis tool, which is called PermaLearn. So at first, you need to search it on the internet by typing PermaLearn. After you clicking this first link, you will see this display, which is separated into three important parts. The last part is show all the functions that are available in order to determine the support reaction, the normal shear bending moment, reverse bending moment, and also the deflection diagram. And this middle part is show the grip where your structural member will be displayed. And this right part is the setting where you can change the grip size, the mesh size, and also the unit system. And now let's begin with the setting. So after you clicking the link, it will automatically set the grip size here to 10 meter x 10 meter. And if you are working with larger project, you need to change the grip size to the size that fit your project. For example, I change it to 30 meter x 30 meter. And for this mesh size and the number of finite element, I will explain it later. And there are two unit system, which is SI unit and BG unit. For SI unit is referring to the unit that have meter, Newton, kilonewton, and for the BG unit, it has feet, inch, and kip. So I change it to BG unit, and then I click Save option. After you change this, don't forget to click Save option. And another reminder, do not click this refresh or clear all. So it will clear all your structure member and also the setting. And now let's moving on to the function. The cross section is the first function where you can input the cross sectional area, the modulus of elasticity, and also the moment of inertia. The second function is member, where you can generate the many structural member as you want. And after you clicking this member function, it will show this four option, which is referring to the begin x coordinate and the begin y coordinate, horizontal distance from this begin point, and the vertical distance from this begin point. So if I want my member to starting from the coordinate, the x coordinate equal to 0 and y coordinate equal to 0, and if I want my member to going to the right, if you want your member to going to the right, you need to put the positive number on this horizontal distance, and if you want it to going to the left, you need to put the negative number. Same as the vertical distance from the begin point. If you want it to going up, upward, you need to put the positive number, and if you want it to going downward, you need to put the negative number. For example, I want my member starting from x coordinate equal to 0 and y coordinate equal to 0 and going to the right 6 feet. Then I'm clicking add. So from point A to point B here is equal to 6. As you can see, x equal to 6 feet. And the starting point here is it has the x coordinate equal to 0 and y coordinate equal to 0. And then I want my point B here to go upward 4 feet. So I need to click join coordinate here to point B. And then I put a vertical distance here to 4 feet because I want it to go upward. And then from point, as you can see here, from point B to point C is 4 feet, y equal to 4. And one more option, if I want point C here to go inclined this way, I just need to click point C here. And if you want it to go incline, you need to put two number, which is the horizontal one and the vertical one. I want it to go into the right 6 and going to upward 6. So it will generate this inclined member. This table is show all the data that we input at the moment, and it also has two functions, which is edit and remove. For the remove, if you want to remove which number, 1, 2, 3 here. If you want to remove the member 3 here, which is referring to the inclined one, you just click remove here, it will disappear. And for this member BC here, if I want it to be, for example, 6 meter, 6 feet, so I just click edit and edit this vertical distance to 6 feet, and then I click edit, it will jump up to 6. And if I want it to go in horizontal, I put the vertical distance equal to 0 and horizontal equal to 6, for example, and then I click edit, it will going back horizontal. And now I want to add another member point C here to going horizontal, for example 9. So we're going horizontal 9. And then for support function is a function where you can add support at the point you want. And there are three support types, which is fixed support, pin support, and roller support. For example, if I want to add point A here to be a fixed support, I just click fixed support and then add. And point C here to be a roller, I just click point C and then click it as a roller. And for hinge function is a function where you can add hinge to the point you want. For example, I want this point B here to be a hinge, so I just click point B and add hinge. As you can see, after you adding the hinge, you will see this small dot, which is referring to the hinge. And if your hinge connected to 3 member, it will show three small dots. And if you want your hinge just connected only one member, for example, I need to click edit and then I remove one member out, which is, for example, I remove member 2, which is this member, and then I click edit. It will remove the connection between this hinge to this member. But it will be wrong for this problem, this type of problem, but it will be right for some type of problem. And now let's moving on to the join load. Join load is a function where you can add a single load to the join to a specific join. For example, we have here join 1, join A, B, C, D. There are 4 join. And join load here is a function where you can add single load to that join. For example, I want to add a join load here at point D. Just click D here. And if I want it to be a horizontal force, to the right I need to put the positive number, and to the left I need to put the negative number. And if I want it to go upward, I need to put the positive number on the vertical force, and if I want it to go downward, I need to put it as a negative number. Also the same as the couple moment. If I want to add a counterclockwise, I need to put the positive number, and if I want to put it as the clockwise, I need to put the negative number. So for example, I want it to be 6 keep to the right at point D, so it will display like this. And if I want to give it to the left, move it to the left, like I just add the negative sign, it will go into the left as compression. And if I want it to going upward, I just change this horizontal to 0 and vertical here to 6. So it will going upward. Same as if I want it, same as the horizontal. If I want it to go downward, I just put the -1. And if I want to add the moment at that point, I just, if the moment is counterclockwise, I put the positive. So I put the positive here, it will generate a counterclockwise moment. And if I want that force to be inclined, I just put another horizontal force here to be -6. So it's going to the left. So it will generate the this horizontal force here. So now let's moving on to the point load. So point load here is a function where you can add the single force or couple moment to the distance where you want. For example, distance from joint C here to joint D here is 9 feet. So if I want to put it at the middle, I just I don't if I don't have any point in the middle here, we need to use the point load where you, well, for example, I want to add the load between this member. I need to click that member. As you can see, it will turn into yellow. And for the load orientation, global coordinate system is referring to this, the coordinate that stick with the whole structure. For example, if the whole structure is um, is uh, is horizontal like this, so it will stick with this uh, horizontal axis. And if the local, and for the local coordinate system, it is referring to this member only, is this member axis only. If this member is inclined, it will follow this member inclined. So from now on, I just click global, and distance from begin load here is referring to the distance from point C here. So if I put it, for example, 5 from point C, and horizontal force the same as the joint load, and vertical force the same as the joint load. So I just add 5, keep, and the moment is -15 to be clockwise. So I just click add. It will generate this force and bending moment between this member, which is from point C here to this point is 5 feet as I input at the moment. And now let's moving on to the linearly distributed load. Linearly distributed load is a function where you can put the distribution load, also the uniform distributed load and the non-uniform distributed load. The same as the point load here, we need to click the member ID. For example, I want to add a uniform distributed load at member 2 here. So I just click the member 2 here. And for the global and local, the same, I stick with the global. And for the load type, there's 2 load type, which is the vertical as it's going like this, or horizontal as it's going like this. So from this, for this structure, I put it as vertical load. And from distance from the begin point, the same as the joint load, which means that distance from point B here to the point where you want to put this load. And distance from the end joint here, which means that the distance from point C here to that load. So I pick distance from point B here to be 1 feet. And the begin load here is the starting load at this location. For example, I want it to be uniform, so I put negative 9 downward, and the end load here also negative 9, which means that from for example, point B here is 6, so this from this 7 feet until this 12 feet, it will generate the uniform distribution load of negative 9. So as you can see here, at this point is x equal to 7, and at this point is x equal to 12. So if I want it to be non-uniform, I just click edit here, but I edit only this begin load equal to 0, and this end load equal to negative 9. So it will be like this. And if you want the rectangle and the right triangle distribution load, you need to edit it and put the begin load, for example, negative 6, and end load is negative 9. So it will generate this distribution load like this, something like this. And now let's start working on some problem that relating to this function. So I click clear all. So our first problem is example 3.9. They ask to compute the reaction for the beam here. So at first we need to build the structure. So since it is using the BG unit, so we stick with the BG unit here. So it doesn't give us any cross section, so we can skip it. And moving on to the member. I want my member to starting from x equal to 0 and y equal to 0. So just moving toward 10, and from point B here going forward 5. From point C here it's going forward 5. From point D here it's going forward 5. And from E here it's going, oh, that's all right, 10 5 5 5. So 10 5 5 5, yes. And then let's start adding the support. So at point A it is a roller. At point C, at point B it is a roller, and at point E it is a pin. Roller at A, roller at B, and pin at E, and also hinge at C. So we need to add hinge at point C. So after this, we already add the support. And now let's add the external load, which is 12 kip and 24 kip at point C and at point D respectively. So the joint load, point C here, we have the downward force of 12, and at point D here, we have the downward force of 24. So after we adding the force here, we can click to the solution. So the solution, we have many options where you can solve the member, the support, the load, the external effect, the reactions forces, the normal forces, the shear forces, bending moments, but in reverse, and also the deformation or deflection. So in this exercise, they ask us to compute the reaction only. So we just click the reaction and unclick this three. So display. So as you can see that AY is equal to negative 12, BY is equal to 36, and EY is equal to 12. So we need to check it with the menu solution book. AY negative 12, BY is 36, and EY is 12. And if you want to show the support too, you can click the support and click it display. So it will show us the support. Roller at A, roller at B, and pin at E. And if you want to show the external load too, you just click the load and then display. So this is our external load, negative 24 and negative 12. And that's it for this problem. And now let's moving on to another type of problem. Clear all. And then this problem is the example 3.8. They ask us to compute the reaction for the beam here by treating the member AB here as a link. So if it is a link, we need to add the hinge at this point B. So at first we need to build the structure member. So I want it to start with x equal to 0 and y equal to 0. It's going to the right 3 and going upward 4 as it is inclined. As you can see, it's inclined. And from point B, it's going toward to the right 3. And from point C, it's going toward 3. It's going toward 7, like this. Because I don't want to make another joint, because I want to give an example of the joint load. And after this, we need to add support. At point A, we have pin, and at point D here, A, B, C, D here, we have pin. And since AB here is a link, so we need to add a hinge at point B. And now let's add the external load or couple moment. We have 20 kip feet at point C as a clockwise. So at point C, we add couple moment negative 20. And we also have a uniform load from point C here to point D here, but we use the point load here, the last member 3 here with the global load orientation, and the distance from the begin point, the distance from point C here is 3 feet, so I click it 3. And oh sorry, it's not the point load, but it's the linear distributed load. I'm sorry. So the same load type is vertical, and the distance from the begin point is 3 from this point joint C here, as you can see here, 3. And the begin load is negative 9 to negative 9. So we will have this uniform distribution load. And then just click the solution and show only these reaction forces. So we get that Cy is equal to negative 3.9, Cx equal to negative 3.9, Cy equal to 30.8, and Ay equal to 5.2, Ax equal to 3.9. Let's check with the solution. So Cy is 30.8, correct, and Cx is 3.9 as it going to the left, so it is negative, and Fab equal to 6.5. But it also equal to the square root of 5.2 square plus 3.9 square, which is equal to 6.5. And that's it for this problem. And now let's moving on to another problem. So in this problem, they ask us to draw the shear moment curve for the beam and also get the deflected shape for this type of beam. So first we need to construct this beam first. So since it is the SI unit, we need to change it to SI unit. They didn't give us the cross section, so we can skip it like before. I want it to, and the member, I want it to start with 0, so it's going to the right 6, and from B it also going to the right 6. And now let's start adding the support. At A we have roller, and at C we have pin. And now let's add the distribution load, which is for member A, global coordinate system, vertical load. And since our load is starting from the begin point to the end point, so we don't need to input this number and also this number. So the begin load is 0 and the end load is -9. So we can get this distribution load. And for member 2, the same here, just the begin load is +9 and the end load is 0. So we can get this. So we can, after this, we already put all the force and the support. So we can jump to the solution and click all, just the shear force, shear diagram. As you can see here, the maximum shear here is -18 and 9 here. So here 9, -18 and 9. So the same as the manual solution book. And now let's move on to bending moment. The maximum bending moment here is 20.25 because we set the mass size equal to 1. So if you want a smoother curve, you need to lower the mass size, for example. And for example, with this mass size equal to 1 meter, the finite of element is equal to 12. And if I change it to 0.5, the finite element will be double, which means that one finite element is equal to 0.5. And if and this beam is 12 meters, so if one is 0.5 meter one element, so 12 meter will be 24 element, as you can see here. And after we change the mass size, we can see that the maximum bending moment is changed, is equal to 20.78 and -0.2078 here. So if we check to the menu solution book, it will be the same, 20.78 and -20.78. And for the bending moment reverse, it just flip the bending moment. And for the deflected shape, it will show the same deflected shape as the menu solution book here. And that's it for this problem. And now let's moving on to another problem, which is the thrust problem. It asks us to determine the force in our bar and indicate it is tension or compression. Now let's build this structure first. It is the SI unit, and I change this equal to 1 and save option. And I want my structure to begin with 0 again, so it's going horizontal to the right. Oh, it is the BG unit, so I need to change it to BG unit back. And it is a larger project, so I need to switch it to 50 feet x 50 feet. It's going to the right 15, and from point A here, it also going inclined to the right 15 and upward 15. So as you can see here, we have the incline 1, and from point B here, it's going upward 15. And from point B here, it's going to the right 15, and from point B here, it's also going to the right 15. From point E here, it's going downward 15, so it's negative. And from point E here, it's going to the right 15 and going downward 15, so it's minus 15. And from this joint C, it's going to the right 15. And now let's add the support. At A, it is a pin. At C here, it is a roller. And at D here, it is also a roller. So now we have roller at D, roller at C, and pin at A. And now let's add the external load. Since it is a single load and we already have all the joints, so we can use the joint load. It will be more easier. So at point B here, we have a downward force of 10. Oh, sorry. Downward force of 10, not the compound moment. And at point F here, we have a horizontal force to the right of 20. At point F here, yes, it have to the right of 20. So at point F here, it is going to the right 20 kip. As you can see here, it will be the same as this structure. So let's jump into the solution. So I want the force in all bar, so it is the normal force. I click display. So it will show that FAF. Oh, I forgot to mention that if you are working with the truss, you need to add hinge to all member. For example, we need to add hinge for member A here, B here, C here, D here, and also E here, and also F here. Only for the truss problem, you need to add all member as a hinge. And now let's jump to the solution back and show the normal diagram. As you can see here, AF here is 30 kip, and this one is also 30 kip, and this one is also 30 kip. Which one? This 30 kip. This F here is 30 kip, and this is 10. 30 kip 10, and BC is negative 10. And for the incline, we have square root of 10 square plus 10 square, which is negative 14.14. This is right. And another one is the square root of 30 square plus 30 square, which is equal to the negative of 42.42. This is right. So by this, we already solved this problem. And now let's moving on to another problem, which is asks us to determine our reaction if we have this incline, and at B here it is a hinge, and we have this uniform distribution load. And now let's build this structure first. I want it to start with 0, and since if BG unit is still stick with the same setting, it's going up 10, and from point B here it's going up 10, and then from point C here it going to the right 20, and it going downward 4 as it is inclined. And from point C here, it's going down 16. And now let's add the support. At A, we have pin. At D, we also have pin. And now let's add the hinge. So we have the hinge at point E. So we add hinge, and then we add the joint load. At C here, we have the force to the right 10 kip, and we also have the uniform distributed load along this member. So we just click the linear distribution, and this is member 1, 2, and this is member 3. Since our force is not the global coordinate system, so we need to change it to local coordinate system, and load type is vertical, and distance from the begin point, we put it 0, and also the end point, since this uniform distribution load is from the begin point to the end point, and it is 0.4 kip per feet going upward. So begin load is 0.4 and end load is 0.4. Click add, so we can have this uniform distribution load. So by this, we already construct our structure member. And now let's click jump to the solution and click the reaction forces. So as you can see, AX is equal to -5, AY is equal to negative negative I'm sorry, I put the wrong location of this pin, so I need to remove it back and then add pin at point B, because I'm moving too fast. I'm sorry. So now let's do it again. The reaction force. So we have AX is equal to -5, AY is equal to -10.44. EX is equal to -6.6, and dy is equal to 2.44. Now let's check with the solution. As you can see here, AY is going down, dy, dx, and ax the same as this menu solution. And now let's move into another problem, and also with another function. So for this problem, it's indicate a new function, which is the temperature change. So at first, we need to input all the 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 data that we have, and then I will explain this function when I reach that function. So it is the BG unit, and it has the cross section of E equal to, and moment of inertia, we don't have it, so we can put the number whatever you want. So I just put 100, and the area is equal to 4. So I think this is too big, so I need to move it equal to 1. And then let's put the member. I want my member to start from 0. No, my member is start from x equal to 0 and y equal to 20. And it's going to the right 15. Oh, I need to select the cross section here. 1, So from point B here, it's going downward -20, and from point C here, it's going to the right 15 and downward -20. And from point D here, from point C, from point, which one? From point A here. Wait, this is point, from point B here, it's going to the left, -25. So, right, and then we need to add support. We have support at C is a pin, and support at B here is also a pin. And now let's add the external load. At point A here, we have the downward load of -80, and from this we already built this structure. And now let's jump to the temperature change, which is a new function where you can add the temperature change to the member you want. For example, if you want, this exercise, they mentioned that the temperature of member BD here is subjected to a temperature increase of 60 Fahrenheit. So which means that member BD here, the inclined one, is increased the temperature by 60 Fahrenheit. So since this website is stick with Celsius, so we don't need to change from Fahrenheit to Celsius. We just need to input the same amount of Fahrenheit, so it will give the 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 same solution as the menu solution book. So example, this incline. So if it is increased, we plug in the positive, and if it is decreased, we plug in the negative. So it is increased 60 Fahrenheit or 60 Celsius, and the coefficient the same as the temperature. If it is given as Fahrenheit, we just put that number. We don't need to convert it to Celsius. So 6.5 10 power minus 6. Just clicking add, and then they will show this sign, which is the temperature change is 60 Celsius, and the alpha, the coefficient, is equal to 6.5 10 power minus 6. And now let's jump to the solution, as they want to see the vertical and also the horizontal deflection at joint C. So we just to the deflection and click display. So at point C here, it's deflect on horizontal equal to 0, and vertical it deflect 0.41 downward. So we need to check the solution. So at the vertical one is 0.41 downward, it's right, and the horizontal equal to 0, which means it is the same as the menu solution book. And now let's moving on to another problem and another function too, which is the example 10.7. They ask us to determine the reaction created when the frame is connected into the support when there are a fabrication error. So let's build this structure first. It is also in BG unit, so we start with the cross section. We have I equal to 240, E equal to 2 here, and since it doesn't give the cross-sectional area, so we can just plug in the any value that you want, and also fixable a fit that fit the moment inertia. So I give it equal to 10, and starting from the member, Our member is begin with x equal to 0 and y equal to 9. And the cross-section ID is 1, 0, and 9. Oh, yes, and it going to the right 18, like this. And then from point B here, it going downward 9. So this is our structure. And now let's add support. At A, it is a pin. And at B, it is a fix. And since there are no additional load, we need to jump into the new function, which is a fabrication error. As they mentioned that the jitter AB of the frame, it's fabricated 1.2 inch too long, which means that this member AB is fabricated too long, 1.2 inch. If it is fabricated too long, we need to put the positive number, and if it is too short, we need to put the negative number for this member AB. So we just click add and then jump to the solution as they want the reaction only. So we just click the reaction and then we click display, which is AY here is equal to negative 5.96 and AX here is equal to 7.9 and MA is equal to negative 35.49 and CX here is equal to negative 7.9 and CY here is equal to 5.9. And if you want it to be more accurate, you need to lower the mesh size. Just for the normal and the shear and bending reverse bending moment. So if we check it to the menu solution book, it will be slightly different, but the error is acceptable. For example, here AY is CY is 5.96 and CX is 7.9 to the left here, and it is 5.9 to upward, and also for the reaction at A, 5.9 downward, 7.9 to the right, and clockwise of 39.7. 35.7. The same here, clockwise, downward, and to the right. And that's it for this problem. And now let's move on to another problem and also another function, which is the tall support settlement. And for this problem, they ask us to determine the reaction for the beam in the figure 9.8 when the uniform load is applied and the fixed support rotate clockwise 0.003 radius and support B set to 0.3 inch and E and I is given. So now let's build the structure first, which is we are working on the BG unit, so we need to change to BG unit, and the grip size is 10. Save option. Now let's input the cross section first, which is E equal to 3, I equal to 240. Cross section, just give random number 10. Then let's add the member. It's starting from 0, 0 and going to the right 8, cross section ID 1, and from point B to the right 2. And then let's add the support at A is a fix, and at B is a roller. Now let's add the uniform load. Number 1, load type is vertical, and begin load is -4 to -4. Since the uniform load is acting from the begin joint to end joint, so we don't need to put the input of this two option. Add, and then another member, the same, -4 and -4. And now let's moving on to the new function, which is support settlement. Support settlement is a function where you can put the settlement of the support only at the support. So in this problem, they mentioned that the fixed support is rotate clockwise 0.003 radius and support B set tall downward 0.3 inch. So we need to input that number. So at support B is set tall downward 0.3. So if it is set tall upward, we need to put the positive number, and if it is set tall downward, we need to put the negative number. And for the fixed support is the same. If it is set tall to the right, we put the positive number. If it is set tall to the left, we put the negative number. And if it is set tall upward, put positive number, and put downward, put negative number. Same to the rotational settlement. If it is counterclockwise, put the positive number, and if it is clockwise, put the negative number. And since it is rotate clockwise, so it is negative 0.003 radius. We need to convert it to degree, which is 0.003 multiplied by 180 and divided by pi, which is 0.171. And now let's jump to the solution. They ask us to find the reaction. So the AY here is equal to 18.46, and by here is A here is equal to, so AY here is equal to 18.46, and A here is equal to 27.6, and BY here is equal to 21.53. And the menu solution book, they found AY is equal to 18.85, A is equal to 30.8, and BY is equal to 21.15. It's a little bit different, but the difference because they change the support settlement at fixed here. They convert it from -0.171 to -0.18, and if we change that to 0.17, it will get a better accuracy. The reason why they change it because the system is automatically convert the digit here to the greater one. If we put 171 here, it will convert to 0.18. So by this, we just put 2 digits here. So it will give us the better accurate, which is AY is equal to 18.87, A is equal to 30.96 counterclockwise, and BY is equal to 21.12, which is slightly different from the menu solution book. Slightly different. So that's it for this video. Thank you everyone for watching this video.